real and imaginary part, and you can calculate, you probably know better than I, how to calculate the reflectivity of the material based on its dielectric constant. The dielectric constant comes from its conductivity as a function of frequency, and that's more or less why you get reflection, because the conductivity is very high. Now you'll notice that not all metals reflect the same colors as well as each other. Silver is like a real mirror. It reflects all visible light equally well, and you can just see yourself in the silver. But gold doesn't reflect some frequencies as well, so it has sort of a yellow color to it. It doesn't reflect greens and blues very well, so what's left over is sort of yellowish or goldish, giving it its beautiful color and its insane value. So the reason for that, the differences in reflection come from the differences in conductivity as a function of frequency. Now, one could take the band structure of one of these materials and calculate from it the conductivity as a function of frequency by looking at all possible transitions of electrons between filled states and empty states. And that does give you a prescription for calculating conductivity, but it's a little bit beyond what we're going to study this year. I'm just going to promise you that this quantity is encoded in the band structure of the material. Now, one more thing about optical properties, which is quite important, is that details matter. And some of the details that matter include the surface of the material. Now, for example, the surface. You know, copper and gold and silver and sodium are all very good metals. But silver and gold are very shiny and reflective, giving them their insane value, whereas sodium looks kind of dark and dismal. And the reason for that has to do entirely with its surface. It's a perfectly good metal. It's just as good a metal as silver is, but its surface actually reacts with oxygen in the air and creates an oxide layer, which is not reflective. So you're actually seeing the surface, not the sodium. So here's actually a picture of a block of sodium that's been freshly cut. And the freshly cut piece of it is very shiny, but you can see the sides of it look rather tarnished. And that's just an effect of the chemistry of sodium. So one has to be careful when one talks about the optical properties of the material. You're really always looking at the surface of the material. A second thing that matters an awful lot is impurities. Matter a whole lot. We'll talk more about impurities in a few minutes. But the reason why impurities matter a lot, let's imagine we have, so here's our band diagram again. So we have some, say we have an insulator, so we have a filled valence band and an empty conduction band. And so we would have some gap, and it will be transparent to any frequency below the gap. But suppose I add some impurities. Well, those impurity atoms can have energy levels that sit inside the gap, in which case a photon of this frequency could create an excitation, h bar omega, okay? And then you can get absorbance of some photon frequencies which are actually below the gap. Now, if I can back up here, a classic example of this is impurities in diamond. So if you add only one boron impurity per 10 million carbon atoms, you give the diamond a rather nice blue color and gargantuan insane value to this diamond for being beautiful and blue. A nitrogen impurity per million atoms gives a diamond a rather nice yellow color. And in fact, you can get lots and lots of different colors to the diamond depending on what kind of atom you put in as an impurity. And the difference in the colors depends entirely on where in the gap the impurity states sit, and so what frequency is absorbed by these impurities. It doesn't take a whole lot. Now, synthetic diamonds can be created in the lab, so of course it's the same thing, it's the same carbon. You can put in any impurities you want, they're cheap, you can make a ring out of it if you want, except for the fact that De Beers has a monopoly on the diamond trade. These things are every bit as good as a diamond that you find on the ground. Okay. My rant against De Beers. Okay, so this is more or less what I want to say about optical properties of solids. So let's try to talk a little bit about what happens when we make these excitations. So here we have, I'm drawing the same picture again and again. Here we have some conduction band, and here, in which you imagine being empty, and a valence band, which we imagine being filled, down here, valence. It may be an indirect gap, it may be a direct gap. This point and this point need not line up. I've actually drawn them to almost line up, that was a mistake. But they could line up, they could not line up, doesn't matter, either one's allowed. Then remember that in this particular configuration, the valence band is completely inert. The valence band doesn't carry any current, it doesn't carry any heat, it has no interesting properties whatsoever until you come in, say, with a photon and you excite an electron out of the valence band up into the conduction band. Like that. Now remember, when you excite the electron out of the valence band into the conduction band, you leave behind an absence of an electron, okay? Which is known as a hole. Hole equals absence of electron, in otherwise filled valence band. And this should be thought of as being entirely analogous to electron-positron creation in the genuine vacuum, the vacuum of space here. The vacuum of space, like the filled valence band, is completely inert. But when a photon of sufficiently high energy comes in, it can pair create an electron and a positron from the vacuum. Similarly here, when a photon of sufficiently high energy comes in, it can pair create an electron and a hole pair from the vacuum. And you should think of these electrons holes as being completely independent particles. So here you have pair creation, and then at some later time, the electron may fall back into the hole. It's known as recombination. And once the electron falls back into the hole, you have the inert filled valence band again. Now there are other ways to get electrons and holes in your system. One way that we discussed last time, again, an energy diagram, we can have our valence band like this, and if our valence band and our conduction band overlap, then instead of having the entire valence band filled and the entire conduction band empty, we'll have a metal where the valence band is, say, mostly filled, and the conduction band is a little filled. So what we're doing here is we're transferring electrons out of the top of the valence band into the bottom of the conduction band because it just happens to lie lower. So overlapping bands also gives free electrons and holes. Okay? Does that make sense? Good? So far so good. Okay, we saw an example of that last time with calcium. Now, let's call the density of electrons equals n. That n stands for negative charge carriers, whereas the density of holes is conventionally called P for positive charge carriers. Now you may notice that in these examples that I've shown here, the number of electrons and the number of holes is equal. If we started with a completely filled valence band and we excite an electron out of the valence band up to the conduction band, then each time we make an electron in the conduction band, we leave a hole behind in the valence band. Similarly, if we start with a otherwise filled valence band, like if we have an even number of electrons per unit cell, but the bands overlap, then the number of electrons that get transferred out of the top of the valence band into the bottom of the conduction band also leaves behind exactly the same number of electrons leaves behind the same number of holes in the valence band as we have electrons now in the conduction band. So we might conjecture, does n equals p all the time? And the answer is yes, if pure, but no, we'll see, if impurities or dopants. So impurities in these materials are known as dopants. Known as dopants because they are sometimes put in intentionally, like other things that are called dopants. So to understand why that happens, let's imagine a case of silicon, which is the world's most important semiconductor. And let's imagine we have a whole bunch of silicon atoms lined up in a lattice, which I'm going to draw as a square lattice because it's the only lattice I can draw easily. So these are all silicon atoms, and silicon is a semiconductor. Pure silicon has a filled valence band, a gap, and then an empty conduction band. Now let's imagine that we take one of these atoms and we replace it. We replace the silicon atom there with a phosphorus atom. Now then we have to go to our handy periodic table, and we notice that phosphorus is one step to the right of silicon. So that means phosphorus equals silicon plus a proton plus some neutrons, which I'm not going to care about, plus an electron. Okay? So we can think of this as being entirely just a silicon lattice, except there's an extra plus charge sitting here. So there's a little plus charge sitting there. And then you have one extra electron that you don't know what to do with. So that one extra electron goes up into the conduction band. So the one electron, the extra electron goes into conduction band. And because of that, phosphorus is known as an N-dopant because it creates electron density the more phosphorus you add. So here's a little cartoon of that, how that happens. So this picture of silicon atoms with these 4 little electrons sitting around it is supposed to represent filled bands of electrons around the silicons. It's equivalent to think of a bunch of bands that are filled. That's an equivalent statement to saying all the electrons are tied up in covalent bonds. That's entirely just a different, more chemical way of saying that all the bands are filled, all the electrons are tied up in covalent bonds. Both of them are a way of saying that the electrons are inert. Then you add a phosphorus atom in place of one of the silicons, and so you have an additional positive charge sitting on that position, and you've also added an additional electron. So that additional electron goes running free in the conduction band, and we're going to come back to wondering about what that additional positive charge does sitting there at that point in the crystal. But I'll tell you right now that the positive charge doesn't do much serious, whereas the negative charge that runs free is actually quite important. Now you can do the same. You can play the same game with something on the back up to the periodic table. Chemically, all of the things in the same column act the same. So instead of phosphorus, I could have used arsenic. Instead of phosphorus, I could have used nitrogen. They all have the same chemical properties. They just have a different number of inner shells, which doesn't really matter much. If I go to the other side of silicon, then what I have is exactly the opposite story. So on the other side, so boron or aluminum, those are like silicon minus a proton, minus an electron. In which case, we get an extra hole, if you want, or a loss of an electron, an extra hole into valence band. So these are known as p-dopants.